Have you ever imagined a planet that looks like Earth from afar, yet hides a story completely its own? Venus shines as the brightest object in our night sky after the moon, but behind that soft glow lies a world of crushing pressure, boiling heat, and endless clouds of acid. Its surface is invisible to our eyes, wrapped in a permanent haze that bends radar and light alike. For decades, we could only guess what waited beneath. Then, orbiters and probes began to peel back the layers, slowly revealing a restless planet that still reshapes itself. If exploring hidden worlds and quiet revolutions in science speaks to you, a gentle like and subscribe helps this journey reach others. Settle in and let's uncover the true face of Venus. Venus is often called Earth's sister because both formed from the same cloud of gas and dust and now circle the sun in nearby lanes. On paper, the match looks close, almost the same diameter, almost the same mass, built from similar rock and metal. The resemblance, however, stops at the surface. Where Earth keeps liquid water and a mix of gases we can breathe, Venus keeps heat and pressure. Its bright face hides a thick blanket of carbon dioxide with clouds made of sulfuric acid. Its ground is a wide sheet of volcanic rock called basalt. Winds high in the atmosphere race around the planet. Near the surface, the air is so dense that motion is slow and heavy. The planet shines like a jewel from far away, yet it is not a gentle world. For a long time, people wondered whether life could exist there, or whether oceans ever covered the low plains. The idea of a runaway greenhouse effect has become the leading explanation. A greenhouse effect happens when a planet's atmosphere traps heat from sunlight. On Venus, it ran out of balance and kept building. If early Venus held water, warming would have increased evaporation, and water vapor itself is a strong heat-trapping gas. More heat means more vapor, which means more heat again. In time, sunlight high in the atmosphere split water into hydrogen and oxygen. The light hydrogen escaped to space. What remained was a dry, heavy atmosphere and a surface sealed under extreme temperature and pressure. Scientists still debate the details, and they test the surface for signs of recent lava flows that would mean active volcanoes continue to vent gas. The questions are simple to ask and hard to answer because the clouds block ordinary light. Spacecraft have bridged that gap. The Soviet Venera landers dared the descent, returning the first images and measurements from the ground before the heat and pressure ended each mission. Radar mapping from orbit later created global maps that cut through the clouds. NASA's Magellan mission, in the 1,990 seconds, used radar to trace mountains, rifts, and wide lava plains, with craters scattered across them. These views showed a world that has been resurfaced in large sweeps, with features that suggest volcanism and possible tectonic motion different from Earth's plate tectonics. Venus became both a laboratory and a warning, a place to study climate taken to extremes and geology under a heavy sky. The idea that Venus teaches us about balance is not only a metaphor, it sits in numbers. Surface pressure is about 90 times that of sea level on Earth. Temperatures on the ground are hot enough to melt lead. Carbon dioxide makes up most of the air, with nitrogen as a smaller part, and traces of sulfur compounds. Clouds form not from water, but from droplets of sulfuric acid that build thick, bright layers. Winds at the cloud tops circle the planet in a few days, a pattern called superrotation. The planet itself spins very slowly and in the opposite direction from most planets, a retrograde rotation. A day on Venus lasts longer than a Venusian year. These facts set the stage for the rest of its behavior, from the way heat moves to the way storms sweep the sky. The story of how two near twins diverged starts in the early solar system. Picture a young sun ringed by a disk of rock, ice, and gas. Over millions of years, small pieces collided, stuck, and grew. Impacts were frequent and violent, large enough to melt rock and throw debris far away. Out of this process came two planets with similar bulk makeup: silicate rock forming their crusts and mantles, iron forming their cores. Earth ended up slightly larger. Venus reached about 90% of Earth's mass and nearly the same diameter. The difference in their orbits is small in distance, but large in effect. Venus orbits closer to the Sun by tens of millions of kilometers, enough to change how much energy it receives and how its atmosphere evolved. During the heavy bombardment phase, comets and asteroids delivered both heat and materials. Many researchers think water reached the inner planets, in part inside icy bodies from the outer system. Venus likely received some of this cargo. Measurements of deuterium-heavy hydrogen suggest that a large amount of water may have been lost over time, which fits the idea of early oceans that later vanished. If that picture is correct, Venus did not start as a dry furnace. It became one through a chain of feedbacks driven by sunlight, gas chemistry, and time. Earth, by contrast, found a stable range where liquid water persisted and carbon moved between air, ocean, rock, and life in cycles that moderate climate. Venus is not the only relative in the inner solar system. Mars, smaller and colder, keeps scars of dried river valleys and ice caps that wax and wane. Mercury, closest to the Sun, is a dense world with a large iron core and a surface battered by impacts. Among these neighbors, Venus stands out because its bulk properties, size, mass, density track so closely with Earth's. If you placed both on a scale, their weights would nearly balance. This is why the twin label has held on in astronomy. Yet sibling worlds do not guarantee similar outcomes. A small shift in distance from the Sun, a different early spin history, or a different pace of volcanic release can push climate one way or the other. Venus shows how little margin a world can have before feedbacks take over. To understand this difference, think about the path from a molten surface to a stable crust and atmosphere. Both Earth and Venus cooled from global magma oceans in the beginning. Both vented gases from their interiors. On Earth, water condensed to form oceans. Carbon dioxide was stored in rocks through weathering and plate tectonics. On Venus, water did not stay for long. Without long-term oceans, and with a slower way to trap carbon in rocks, the atmosphere stayed rich in CO2. Once the balance tipped, heat rose and stayed. The clouds grew thick and bright, reflecting much sunlight, yet the heat already stored could not escape efficiently through the opaque, lower atmosphere. The result is a planet locked in a hot, high-pressure state. There is also the way Venus looks from our vantage point. It is the brightest planet in our sky, often outshining every star. That brightness comes from its high albedo, which means it reflects a large fraction of the sunlight that hits it. The thick cloud deck scatters light very well, acting like a mirror. Distance plays a role too, but even when Mars comes closer to Earth, Mars does not match Venus in brilliance. To the eye, Venus appears as a steady point that can cast a faint shadow on very dark nights. Under clear conditions and with careful guidance, observers can find it in daylight as a small, brilliant dot. near the Sun's path. Venus keeps close to the Sun in our sky because its orbit lies inside Earth's orbit. You will not see it overhead at midnight. Instead, you will find it near the horizon after sunset or before sunrise. These positions gave rise to the old names Evening Star and Morning Star. The cycle follows a clear pattern. Venus orbits the Sun in about 225 Earth days. Because Earth also moves, we see Venus swing east and west of the Sun over a cycle of about 19 months as viewed from Earth. When Venus is west of the Sun, it rises before dawn. When it is east of the Sun, it lingers after dusk. It becomes one of the first lights to appear in the evening and one of the last to fade in the morning. Ancient observers tracked this pattern long before telescopes. In Mesopotamia, records tied Venus to deities of love and war, showing respect for its changing role in the sky. The Greeks and Romans kept those links and gave the planet the name we still use. Some early thinkers thought the morning and evening stars were two different objects until repeated patterns made the identity clear. Far away in time and place, the Maya measured Venus with great precision and built tables that predicted its appearances. They tied these cycles to events on Earth because a regular sky offered a way to mark and plan. Across the Pacific and the Americas, navigators and storytellers used Venus as a guidepost and as a character in oral tradition. The common thread is attention. A bright, reliable light invites careful watching. Today, even a small telescope shows that Venus is not a star-like point at all, but a tiny disk with phases. Like the Moon, Venus shows a crescent, half, gibbous, or nearly full shape, depending on its position relative to the Sun and Earth. When Venus is on the far side of the Sun, it appears small and nearly full because we see most of its sunlit face from far away. When it is between Earth and the Sun, we see a thin crescent that looks larger in apparent size because the planet is closer to us. This changing shape is a simple geometry lesson drawn on the sky. It also explains why brightness changes over time. Phase and distance shift together. The clouds that make Venus bright also hide its surface. Visible light cannot reach the ground and return to our telescopes. That is why radar has been so important. Radar sends radio waves that can pass through clouds and bounce off the surface. From the returning signals, we can build maps. These maps show volcanoes, broad plains, ridges, and ring-like coronae that may mark places where hot material pushed up from below. Impact craters appear across the planet, but not in the high numbers seen on Mercury or the Moon, which hints that the surface has been renewed in geologic time. Whether that renewal is steady or episodic is an active question. Venus's rotation and atmosphere shape its weather in ways that are different from Earth's. The planet spins very slowly and backward relative to its orbit. High above, winds zip around the globe in a few Earth days. Lower down, the air is so dense and hot that near-surface winds are limited. Lightning has been reported by some missions. Other instruments have argued against it, and the debate continues. Chemical cycles in the clouds build and destroy sulfuric acid droplets. Sunlight and the atmosphere's chemistry create a layered structure with a cool cloud deck above a hot lower atmosphere. All of this sits over a surface kept at roughly the same high temperature day and night because the thick air moves heat efficiently. When scientists compare Venus and Earth, they pay attention to these processes because they teach us about climate limits. On Earth, water vapor, carbon dioxide, clouds, oceans, ice, and life form a set of linked feedbacks. Some of them cool the climate, some warm it. Over long spans, plate tectonics and weathering lock up carbon in rocks and then release it again. On Venus, without deep oceans and with a different surface cycle, the feedbacks lined up toward warming. The lesson is not a direct prediction for Earth, but a boundary case that helps define what is possible. It shows that a rocky planet of Earth's scale can hold a steady state far hotter than ours if certain conditions apply. Venus's cultural role stays relevant because human attention is a kind of data. A bright body that keeps time with sunrise and sunset becomes a sky clock, and many cultures used it that way. Today, the myths give way to measurements. Venus's mass, diameter, and density sit close to Earth's. Its thick carbon dioxide air explains the bright clouds and hidden surface. Its orbit explains phases and the morning-evening swap, and spacecraft add the details our eyes can't reach. Each piece links to the next, turning a familiar outline into a world that is recognizable in numbers, but foreign in practice. At dusk, someone might still mistake Venus for a plane because it is so bright and steady. Binoculars hint at a disk. A small telescope shows phases. Watching night to night reveals its drift among the stars and its shift from evening to morning object. These simple checks tie everyday sight to probe and radar results, closing the loop between what the eye notices and what instruments confirm. The pattern behind those sights is regular. Venus returns, disappears in solar glare, and returns again on a timetable set by its orbit. Long before clocks, people tracked that cycle. Farmers treated a dawn rise as a seasonal cue. Writers leaned on its steady reappearance as a plain image for renewal. The same rhythm still works. A bright point near the horizon, at twilight, that links quiet observation to a mapped, measured sky. The visual draw is strong, but the science is clear. Venus is bright because its clouds reflect sunlight well. Astronomers call this reflectivity albedo. The clouds act like a mirror, sending much of the incoming light back towards space. To our eyes, that mirror makes the planet stand out against both evening blue and night black. The effect is simple to detect, even from a city sidewalk. It does not require a telescope, only a habit of looking up at the right times. A closer look moves from the sky to the air. The atmosphere of Venus is the core of its difference. It is mostly carbon dioxide over 96%, with nitrogen as a minor component and traces of sulfur gases. Carbon dioxide traps heat. On Earth, it accounts for a small share of our air, measured in parts per million. Yet even that small share makes a measurable difference. On Venus, it is the air. The result is a thick thermal blanket. Heat arrives from the sun, the surface warms, and the atmosphere prevents that heat from escaping efficiently. This is the greenhouse effect taken far past the range we know on Earth. The cloud layers add two more facts. First, they are rich in sulfuric acid droplets, formed when sulfur gases react with water and sunlight high above the surface. Second, they create a bright, high cloud deck that reflects sunlight, which is why Venus shines so much to our eyes. Beneath that deck, the story changes. Light in, heat trapped. The lower atmosphere is hot and dense, and thermal radiation from the surface is absorbed and re-emitted many times before any of it can leak away to space. The whole system rests in a hot equilibrium. A familiar analogy helps. A parked car in sunlight. Light enters through the windows, warms the seats and dashboard, and the interior heats up because the heat does not escape quickly. Now scale that up to a planet. The physics is the same, but the numbers are larger and the feedbacks are stronger. Water vapor is itself a greenhouse gas. If early Venus had surface water, warming would have increased evaporation. More vapor would have trapped more heat. That, in turn, would have driven more evaporation. The loop can run until the surface loses its liquid water reservoir. Once the water is gone, there is no ocean to absorb carbon dioxide and no easy path to lock it into rocks. The atmosphere thickens. The pressure at the surface rises to about 90 times Earth's sea level pressure. Temperatures settle above 460 degrees Celsius. Measurements suggest this dry state came after a loss of water to space. High in the atmosphere, sunlight can split water molecules. Light hydrogen atoms then escape more easily than heavier oxygen. Over long spans, a planet can bleed water upward and outward. On Earth, oceans and a carbon cycle slow these changes. On Venus, the balance went the other way. Without oceans, there was no large-scale sink for CO2. Without plate tectonics that cycles carbon between the mantle and surface the way Earth does, there was no strong geologic break. The atmosphere stayed thick. The clouds have their own weather. Upper winds race around the planet in only a few Earth days, a pattern called superrotation. These winds move the cloud tops quickly while the planet itself turns very slowly and in the opposite direction from most planets. A day on Venus, one full spin takes longer than a Venusian year. Near the ground, the air is so dense that wind speeds are lower, but any movement carries great force because the air has so much mass. Lightning is debated. Some instruments have reported signals that could be electrical discharges. Others have not confirmed them. If lightning does occur, it would be part of the atmosphere's energy budget, as it is on Earth, but in a very different setting. Acid clouds create another cycle. Sulfuric acid droplets can fall as rain from the upper layers, but the heat below causes them to evaporate before they reach the ground. The result is rain that begins and then turns to vapor. The cycle continues without wetting the surface. It is not a comforting rain either. The droplets are corrosive. Any unprotected material would degrade quickly. The word rain, in this case, describes a process, not relief. Entering the atmosphere would be a sequence of changes in light, color, and force. From orbit, the planet looks like a smooth, pale sphere with subtle bands. With descent, the view shifts to a filtered orange glow because the thick air absorbs and scatters sunlight. Contrast drops. Shadows soften. By the time one nears the surface, the sun becomes a dim disk. The air itself is the most immediate challenge. At 90 atmospheres of pressure, a person could not breathe or even expand a chest. Machines need thick shells, strong seals, and internal cooling just to function for a short time. The Soviet Venera landers were built like deep-sea craft and still survived only for tens of minutes to a couple of hours on the ground before failing. The record is short because the demands are constant. High pressure, high temperature, and reactive chemistry all at once. Electronics must be insulated. Bearings must be chosen for heat. Every surface must be protected from corrosion. Even then, the environment wins in the end. Mission design for Venus becomes an exercise in accepting short lifetimes and capturing as much data as possible before systems shut down. Pressure is easier to grasp by comparing it to water. In Earth's oceans, pressure rises by about 1 atmosphere every 10 meters of depth. To match Venus's surface pressure, one would need to descend to roughly 900 meters underwater. Few divers ever reach such depths. Submersibles do, and they are built with careful engineering margins and safety factors. Venus demands the same approach. except the ocean is the air itself, and it is hot. The sky presses like water and burns like a furnace at the same time. Sound would travel differently, too. Dense air changes how sound waves move. Voices would not carry in a familiar way. The tone would shift, and the distance would shrink. The ground would look muted through the haze. Rocks and ridges would sit in a low contrast scene. Without clear blue sky or sharp shadows, the landscape would feel compressed. The color palette would lean toward browns and oranges. None of this is guesswork for effect. It follows from the known optical and physical properties of dense, hot, particle-laden air. Wind at the surface is a slower flow than at the cloud tops, but momentum still matters. A modest breeze in such dense air can push with force. Sand and dust move differently under that load. Erosion patterns differ. Engineers must account for this when thinking about landers or rovers. A design that works on Mars will not necessarily work on Venus. Cooling is the main problem on Mars. Pressure and heat are the main problems on Venus. Mars is hard in cold and dust. Venus is hard in heat and weight. Distance does not set the challenge level. Venus is closer and easy to reach in terms of travel time, but staying and working there is more demanding. Some mission ideas shift focus to the upper clouds, where pressure and temperature are far less extreme. Balloons or aerobots could drift at altitudes where the environment is closer to Earth's. Instruments could sample gases, look for chemical clues, and map winds. The surface would remain out of reach to such craft, but the data from the clouds could answer questions about the planet's chemistry and climate history. The history of brightness in our own sun also plays a role. The sun was dimmer billions of years ago. That matters because a dimmer sun gives a hot planet more room before it crosses key thresholds. Over time, the sun brightened. A planet on the inner side of the habitable zone could then slip past a point where water stays liquid. Once past that point, feedbacks can amplify change. Earth sits near the inner edge of the zone, but has held liquid water for billions of years because oceans, weathering, plate tectonics, and life all act to stabilize climate within limits. Venus passed the edge and did not return. Geology under such an atmosphere follows different paths. The surface is mostly basalt, solidified lava. Radar mapping shows broad plains, shield volcanoes, and features called coronae, which are circular or oval patterns that may mark upwellings of hot rock from below. Impact craters are present, but fewer than on heavily cratered bodies like Mercury or the Moon, which suggests a surface renewed within the last few 100 million years. Whether that renewal is steady or happens in bursts is still under study. Without plate tectonics as we know it, heat may escape in large episodes. If resurfacing occurs in pulses, then long quiet spans are broken by active periods when lava pours out and erases older terrain. Chemistry in the air influences what rocks do at the surface. Minerals react with sulfur-bearing gases. Weathering is not driven by liquid water as on Earth, but by hot, dense gas. The result is a different set of stable minerals at the topmost layer. Some compounds that are common on Earth would not last. Others would form instead. These are not abstract points. They matter for how radar signals reflect from the ground, how heat is emitted at certain wavelengths, and how future instruments should be tuned. The slow retrograde spin sets the length of the day and affects atmospheric flow. Because the planet turns so slowly, solar heating has more time to warm the day side. Yet the dense atmosphere transports heat effectively, so surface temperatures do not vary much between day and night. The uniformity is striking. Poles and equator are all hot. weather patterns exist, but they play out within a narrow thermal range at the ground. The stark contrast between cool cloud tops and hot, low atmosphere defines the vertical structure. Comparing Venus and Earth is not only natural, it is useful. The same physical laws govern both. The differences reveal which processes are key for habitability. Water acts as a thermostat on Earth. Carbon moves among air, ocean, and rock. Plants and microbes take part in that exchange. Tectonic plates recycle crust and release gases. On Venus, the thermostat broke. Without oceans and with a different style of interior surface exchange, the climate moved to a hot, stable state. The lesson is not alarmist. It is a boundary condition for rocky planets of this size. Observing Venus from Earth remains simple. Find it after sunset low in the west, or before sunrise low in the east. Watch over weeks and notice how it shifts from evening to morning object. Through binoculars, its steady light stands out against twilit color. Through a small telescope, the phases appear. A small full disk when far, a larger crescent when near. The change in apparent size and shape follows simple geometry in the Sun-Venus-Earth triangle. Each view is a check on the model built from spacecraft data and physics. The sky and the measurements match. The continuity between culture and science comes from repeatable patterns. Ancient records tracked the same cycle we see today because orbital mechanics do not wander on human timescales. The meaning that people attach to those patterns can vary, but the motions remain. In that sense, Venus provides both a steady light and a consistent set of facts. Its role as morning and evening object is a matter of position. Its shine is a matter of clouds. Its heat and pressure are a matter of composition and feedback. Each point is testable. Looking down through the cloud deck is not a cue for drama, but a way to sort layers. Bright, reflective tops, cooler sulfuric acid mists, a deep, hot column of CO2, and rock under immense weight. Pressure here is not metaphor but math force per area. At roughly 90 Earth atmospheres, each square centimeter bears about the weight of a person. Spread that across a body, and survival needs armor. Machines face the same numbers, which is why landers fail fast. Platforms higher up look practical. The load eases, lifetimes grow, and instruments can sample the chemistry that sets the planet's behavior. Distance from the sun, the amount of starting water, the way heat moves out of the interior, and time all shaped the result. No single factor explains Venus. The combination does. Two planets can begin alike in size and materials, yet small offsets push them toward different end states. Studying Venus next to Earth gives a built-in control. Same physics, different initial and boundary conditions, two clear outcomes. To stand there, if protection made it possible, would not feel like open air. It would feel like the bottom of a hot, invisible ocean. Pressure from all sides. The sun a dull patch behind a permanent veil. Night would not cool the ground. Wind would not refresh the air. Heat and weight would define every moment. That contrast with Earth near twins that diverged shows how narrow the path is between a world that keeps life and a world that cannot. Rotation adds another layer to that difference. Most planets, including Earth, spin from west to east. Venus spins the other way. This backward motion is called retrograde rotation. It flips the daily path of the sun. On Venus, the sun appears to rise in the west and set in the east. The spin is not only reversed, it is slow. One full rotation takes about 243 Earth days. A Venusian year, the time to orbit the sun, lasts about 225 Earth days. That makes a Venus day longer than its year. The long day changes how time plays out on the surface. Because the planet rotates so slowly and the atmosphere is so thick, daylight and darkness crawl by. A sunrise would unfold over weeks, climb through a dim orange sky, and linger before the slow descent into night. Twilight would stretch, not for minutes, but for much longer. As light spreads and scatters through heavy air, night would then extend for months before the next slow dawn. There is also the difference between a rotation day and a solar day. A solar day measures the time from one noon to the next. On Venus, this interval is about 117 Earth days. The retrograde spin and the motion around the Sun work together to shorten the Sun-to-Sun cycle, even though the physical rotation is longer. The math is unusual compared to Earth, but the result is clear. The rhythm of sunlight on Venus does not match the length of its spin. Why Venus rotates backward remains an open problem with plausible paths. A giant impact early in the solar system could have changed the spin. Over long times, the Sun's gravity and the thick atmosphere could also have slowed and reversed the rotation through tidal effects. The outcome may be a mix: a large collision to reset the spin, followed by gradual shaping by sunlight and atmospheric tides. However it happened, the present state is stable enough to last. A slow, backward spin links to the way the atmosphere moves. Near the surface, the dense air creeps along. Far above, winds rush around the planet in only a few Earth days. This fast, high-level flow is called superrotation. It carries cloud tops around the globe many times faster than the ground moves beneath them. From the surface, the wind might feel weak, yet each small gust has punch because the air is heavy. Aloft, the winds tie the planet's weather into a band that circles again and again. These motions affect heat. Venus is hotter than Mercury. Even though Mercury is closer to the Sunday, Mercury has almost no atmosphere, so heat comes and goes with daylight. Venus has an atmosphere made mostly of carbon dioxide, over 96%, so heat is trapped. Sunlight reaches the surface, warms rock, and the rock emits infrared radiation. Carbon dioxide absorbs that radiation and re-emits it in all directions. The process repeats many times before any energy escapes to space. The result is a strong greenhouse effect and a surface temperature around 460 degrees Celsius almost everywhere. Because the air is dense and moves heat efficiently, temperatures do not vary much between day and night or between equator and pole. Mountains are not much cooler than lowlands. The globe behaves like a single thermal system, locked into a hot state. In numbers, the surface pressure is about 90 times Earth's sea level pressure. That is similar to the pressure almost a kilometer below the surface of Earth's ocean. Metals such as lead would melt. Many common materials would soften or fail. The way Venus reached this state likely involved feedback. If early Venus had liquid water, warming would have increased evaporation. Water vapor is a greenhouse gas, which would have added more warming, which would have driven more evaporation. As water rose to high altitudes, sunlight would have split some of it into hydrogen and oxygen. Hydrogen, being light, escapes more easily to space. Over long spans, this leaves less water behind. Without long-lived oceans, there is no major sink for carbon dioxide, no large-scale weathering cycle to lock it into rocks, and no plate tectonics that mirrors Earth's long carbon cycle. Carbon dioxide then accumulates, pressure rises, and the greenhouse effect strengthens. Comparisons help set the scale. On Earth, the greenhouse effect keeps the average surface temperature far above what it would be with no atmosphere. Oceans absorb and release heat, plants and microbes move carbon, and plate tectonics recycles gases. These linked systems limit swings. On Venus, the linked systems pushed in the other direction or were absent. The greenhouse effect ran away and settled into a new steady state. Steady here does not mean gentle, it means constant. This constancy influences geology. Radar maps show broad basaltic plains, shield volcanoes, long ridges, and circular features called coronae that may mark upwelling from beneath the crust. Impact craters are present but not dense, implying that resurfacing has happened in the last few 100 million years. The mechanism may be episodic, with heat building under the crust until large eruptions reset wide areas. In such heat and pressure, rock-air reactions differ from Earth. Hot, dense, acidic gases alter minerals at the surface in ways we would not see at home. All of this lies under a cover of clouds that give Venus its brightness. These clouds are not water clouds. They are made of sulfuric acid droplets formed when volcanic sulfur gases and water traces react under ultraviolet light. The cloud layers begin high and run deep. They reflect sunlight well, which is why Venus shines so strongly in our sky. The same layers also stop visible light from reaching the ground and returning, which is why radar is used to map the surface. The acid clouds participate in a cycle that never finishes at the ground. Droplets can grow and begin to fall, but the lower atmosphere is so hot that they evaporate before hitting the surface. The cycle loops. Gases rise, acid forms, droplets fall, heat turns them back to vapor, and the process starts again. It is a rain that starts and vanishes in midair. At the surface, nothing gets wet. Light behaves differently inside this cover. Shorter wavelengths that make Earth's sky blue do not dominate. The thick carbon dioxide and acid droplets scatter and absorb light so that the ground sits under a dim, yellow-orange glow. Shadows are soft. The sun appears as a pale disk, not a sharp orb. The scene is more like a long twilight than a bright day, yet the heat remains intense. Color and temperature separate in a way that feels counterintuitive. Pressure is a number, but it also shapes experience. At Earth's sea level, the air presses with about 1 kilogram per square centimeter, matched by the pressure within our bodies, so we do not feel crushed. On Venus, the pressure is about 90 kilograms per square centimeter. A human chest could not expand against that load. Machines must resist it with thick shells and careful seals. The Soviet Venera landers carried such protection and still lasted from tens of minutes to a couple of hours before electronics failed. Designing for Venus is similar to designing for deep-sea conditions, except the medium is hot, reactive gas instead of water. Sound would also change. Dense air lets sound travel, but it alters pitch and distance. Voices would not carry as far. The landscape would feel muted, not silent like the moon, but heavy. Vision would be limited by haze. Objects far away would blur. Even nearby, edges would lose contrast. The ground is mostly basalt, formed by ancient flows. A person could not walk there in any normal sense. Heat and pressure would stop the attempt before it started. The slow spin makes the planet's internal rhythm different from ours, but the orbit remains regular. Venus still follows a predictable path around the Sunday. From Earth, we still see it swing from evening to morning object on a schedule we can chart. Galileo's view of its phases told early astronomers that it orbits the Sunday. Later work showed the backward spin and the super-rotating winds. Radar mapped the land under the clouds. Each method adds a piece to a consistent model. It is common to compare Venus with Mercury to explain why Venus is hotter. Mercury receives more sunlight per square meter, but loses heat quickly because it lacks air. Daylit terrain on Mercury becomes extremely hot, and then nights freeze. Venus receives less sunlight per square meter, but traps what it gets. The greenhouse effect keeps energy in the system, and the dense air spreads it around. The result is a higher, more uniform surface temperature. Science fiction once imagined Venus as a wet, cloud-hidden jungle. Measurements replaced that picture with a dry, high-pressure desert. Instead of water rain, there is acid mist that evaporates. Instead of a blue break in the sky, there is an unbroken canopy. Instead of a cycle of seasons, there is a locked state. The change from guess to data is a familiar path in planetary science. Start with what seems likely from a distance, then update when probes and physics provide better answers. The backward spin remains a useful reminder that planets do not owe us familiar patterns. A giant impact early on, or slow tidal forces, or both, can set a world on a different track. Once that track is established, other processes respond. Atmosphere, temperature, winds, and geology. Venus shows one outcome, Earth shows another. Both obey the same rules. Small differences in starting points and energy flows can lead to very different steady states. From a practical side, these facts guide future missions. Surface craft must accept short lifetimes or carry advanced cooling. Electronics may need to operate at high temperatures or be insulated heavily. Materials must resist acid and heat. Airborne platforms at higher altitudes offer longer operation where pressure and temperature are milder. Instruments there can sample gases, trace winds, and test ideas about chemistry and climate history. Each approach trades reach for time or time for reach. The cloud chemistry begins with sulfur dioxide rising from below, reacting with traces of water under sunlight to form sulfuric acid. Droplets grow by condensation and by colliding with smaller droplets. They drift, settle, and evaporate lower down. The constant production and loss sets up layers with different particle sizes and densities. These layers set how much light is reflected, what wavelengths escape, and how heat is transported vertically. Models that match these layers also match what spacecraft see in brightness and temperature profiles. At the surface, the rocks glow in infrared, sending heat upward that the thick air quickly swallows. Only at certain wavelengths, where carbon dioxide absorbs less strongly, can a small fraction of that radiation slip through. Spacecraft have used those narrow windows to estimate surface temperature and to search for change over time. A region that brightens or dims in those bands could mark new lava. The case for active volcanism remains under review, but the method itself proves how physics can reach through layers of cloud and pull out traces of what happens below. Questions about habitability circle back to altitude. Near the ground, pressure, heat, and chemistry exceed every known limit for life. Higher up, in a band where air thins and cools, conditions edge closer to Earth-like pressure and temperature, though the atmosphere is still bone dry and steeped in acid. Some researchers have proposed probes to drift through those layers and test for complex molecules. Life as we know it would need liquid water and chemical stability, so the odds are small. Yet exploring that region would sharpen our understanding of how atmospheres behave and what kinds of chemistry they sustain. Meanwhile, Venus continues its steady roll in our own sky, always near the sun. It brightens before dawn or after dusk, waxing and waning in phase like a miniature moon. Its apparent size changes as it swings toward and away from Earth. Those simple patterns reflect the deeper structure. Orbit controls visibility. Reflectivity sets brightness. Atmosphere determines color and heat. And rotation drives the rhythm of its winds. Each part fits the others, giving a clean, physical picture of how the planet moves and glows. For spacecraft, entering that beauty is an assault. The clouds are thick with droplets of sulfuric acid that corrode metal, etch glass, and blur optics. Instruments need protective coatings, but even those erode. Electronics must survive constant humidity and the charge of moving particles. Cameras lose contrast as haze scatters light. Signals spike as winds buffet and acid gnaws at sensor windows. Missions last hours or days at most, yet those brief encounters keep adding detail. They show chemical cycles that repeat and cloud layers that remain stable over time. What seems like chaos from afar resolves into a system balanced under heat and pressure, a planet maintaining the conditions it created. The visual impression would be unlike any sky on Earth. Think of a steady amber light, as if late afternoon never ends. Haze blurs the horizon. Shadows have soft edges. Distant shapes fade into brownish gold. The beauty is real, even if the chemistry is harsh. From above, the planet glows as if lit from within, because the high cloud deck reflects so much sunlight. That glow is what makes Venus so bright to us at dusk and dawn. It is a lantern in orbit, even while the scene beneath that lantern is unforgiving. Comparing clouds across worlds sharpens the contrast. On Earth, clouds condense from water vapor, fall as rain or snow, feed rivers, and return to the sky. They shape climate by reflecting sunlight and by trapping heat, but they also deliver fresh water to land. On Venus, droplets form from sulfuric acid produced when sulfur dioxide and traces of water react under ultraviolet light. The clouds do not part to reveal blue. They do not deliver water to the ground. Droplets grow, begin to fall, then evaporate in the hot lower air before reaching the surface. The cycle loops above a dry landscape. Clouds become a barrier, not a supplier. This difference matters beyond our solar system. Many exoplanets found close to their stars are rocky or slightly larger than Earth. Some will be hotter than any world here. Others will have thick atmospheres. A super-Venus is a useful category for these cases. Similar physics, scaled up, the sulfur-rich chemistry and persistent haze on Venus provide a template for how light passes through and reflects from such atmospheres, what spectrotelescopes should expect, and how surface conditions may be hidden by clouds. Studying one nearby, well-measured example makes it easier to interpret distant signals that come as tiny changes in starlight. The mask of clouds forced scientists to use radar to see the ground. Radio waves pass through the haze and bounce off rocks, letting orbiters build maps. NASA's Magellan mission in the 1,990 seconds produced global coverage at high resolution. The images showed a surface dominated by volcanic features, broad plains of basalt, long lava channels, and large shield volcanoes. More than 4/5 of the mapped surface sits on volcanic rock. Where the Moon records billions of years of impacts, Venus shows fewer craters, which implies that lava flows or other processes have resurfaced wide areas within the last several 100 million years. Volcanoes on Venus do not line up along plate boundaries the way they do around the Pacific Ring of Fire on Earth. They appear over hotspots, places where heat rises from deep in the mantle and melts rock near the surface. The result is broad shield volcanoes with gentle slopes, built by many fluid lava flows. Ma'at Mons is one of the largest, rising about 8 kilometers above the plains and spreading across a region big enough to cover a country. Around many shields lie sheets of solidified lava that run for hundreds of kilometers. Wrinkle ridges cut these plains, as if the surface skin contracted after cooling. Other features speak to processes we do not see here. Pancake domes form when thick, viscous lava oozes outward and stalls, creating broad, flat mounds with steep edges. Coronae are large, circular, or oval structures, hundreds of kilometers across, with rings of fractures and ridges. They likely mark places where hot material pushed upward from below, bulged the surface, and then collapsed. The distribution of coronae hints at a planet venting internal heat in pulses or patches rather than along shifting plate boundaries. Evidence for recent volcanism has grown. Some radar images suggest changes in certain vents and lava fields over spans short enough to count as geologically recent. Measurements of sulfur dioxide above the clouds have varied over time in ways that could match bursts from eruptions. Small thermal windows in the infrared allow instruments to glimpse the surface glow. Changes there could indicate new lava. Each line of evidence has uncertainties, but taken together, they keep the question open. Venus may still be active. Mountains add another set of clues. Maxwell Montes, the tallest range, stands nearly 11 kilometers above the mean surface level. In radar images, the peaks appear bright, not because of snow, but because something at high altitude reflects radio waves strongly. One candidate is a metallic compound, such as lead sulfide, that condenses under those conditions, forming a thin frost. Metal frost is a phrase that sounds like fiction, but it follows from temperature, pressure, and chemistry at altitude. The physics does not require water. It requires saturation of certain vapors and a surface on which to deposit. Between plains and mountains lie tesserae regions crisscrossed by ridges and valleys that intersect at multiple angles. They are among the most rugged terrains on Venus, and may be among the oldest. Tesserae look like wrinkled fabric laid over bedrock. Their complexity suggests long periods of compression, extension, and shearing in different directions. On a planet without plate tectonics as we know it, Tesserae record stresses that built up and released in local ways. They act as time capsules in a landscape where younger lava has covered much of the past. The highlands called Ishtar Terra and Aphrodite Terra stand out on global maps. Ishtar Terra, near the north, is roughly the size of Australia and contains Maxwell Montes. Its fractured terrain and bright radar returns mark it as different from the surrounding plains. Aphrodite Terra is far larger, stretched along the equator for more than 10,000 kilometers, with ridged, blocky features that hint at broad uplift and extension. Because Venus has no obvious plate boundaries, these continent-like blocks must have risen by other means. Mantle plumes can push up wide areas. Thickening and buckling of a strong lithosphere can build plateaus. Both processes leave patterns we can see in radar. The lack of plate tectonics is one of the biggest differences from Earth. On our planet, water at depth weakens rocks, lubricates faults, and helps the crust break into moving slabs. Those slabs sink, rise, and slide past one another, recycling oceanic crust, building mountains, and regulating carbon over geologic time. Without oceans, and with a hotter surface, Venus's lithosphere appears stronger and more continuous. Heat then escapes, not through a global conveyor of plates, but through widespread volcanism and regional deformation. Highlands that look like continents by shape need not have the same origin as continents here. Taken landscape by landscape, the surface of Venus reads like a record of internal heat trying to get out. Plains of basalt freeze wide floods. Shield volcanoes build up over fixed sources. Coronae mark pulses from below. Tesserae show where the crust bent and broke in patterns that shifted over time. Erosion by liquid water is largely absent, so features remain until buried or distorted. Aeolian processes the work of wind act differently in the dense air near the ground, moving fine particles but not carving deep canyons. The timeline, instead of being written by river valleys and ice sheets, is written by eruptions and tectonic stress. Cloud chemistry completes the picture overhead. Sulfur dioxide rises from the lower atmosphere, reacts with trace water under ultraviolet light, and forms sulfuric acid droplets. These droplets grow by condensation and collisions, settle, and then evaporate in the hotter layers below. That cycle sets up distinct cloud decks with particles of different sizes and densities. The decks control how much sunlight is reflected and at what wavelengths the atmosphere is transparent or opaque. Instruments tuned to those wavelengths extract temperatures, winds, and composition as profiles through the air column. Operating hardware in this environment demands trade-offs. At the surface, landers must survive pressure, heat, and chemistry. Insulation buys minutes. Phase change materials buy more by absorbing heat until they melt. Thick titanium or steel shells hold back the air, but add mass. Windows cloud over as acid attacks surface coatings. Bearings seize as lubricants fail. Designers accept short lifetimes and plan dense sequences of measurements. Higher up, conditions are kinder. Balloons and aerostats can float where pressure and temperature approach Earth-like values, though the acid remains. Platforms there can ride the winds, map their speed, and sample the gases over long paths. Superrotation rules the upper sky. Winds at the cloud tops can exceed 360 kilometers per hour and circle the planet in about 4 Earth days. The ground below takes 243 days to turn once. The air laps it many times. The mechanism is complex. Solar heating creates day-night contrasts in the upper atmosphere. Waves and tides in the air, driven by heating, and by the slow rotation, transport angular momentum upward and toward the equator. Friction with the surface is weak at those heights, so the flow can persist. Once established, the circulation helps maintain itself by feeding back on the temperature pattern that drives it. From the ground, a person would feel only sluggish movement because the near-surface air is so dense. A breeze of a few meters per second in such heavy air carries force, but it does not whip flags or sway trees. There are no trees to move, and cloth would char and fail. Dust would shift under a slow push. Sand would creep. At altitude, the story changes. Images from orbit show long streaks and waves in the cloud tops. These features act as tracers, giving wind speeds and directions. They rise and fade, but the overall flow holds on its fast path around the globe. The same winds set how acid droplets move and grow. Fast horizontal transport means particles experience a range of sunlight and temperatures as they travel. Microphysics, how droplets nucleate, grow, and evaporate, matters for the size distribution, and the size distribution matters for reflectivity. That is why models of Venus's climate include both large-scale circulation and small-scale droplet physics. Matching both is how we test whether we understand the system. Surface features can influence the flow aloft, even through the thick air. Mountains push against the atmosphere and generate waves that rise. On Earth, these are called mountain gravity waves. On Venus, they have been seen in temperature and brightness patterns over high ground. The waves can reach the cloud tops and imprint large stationary arcs in images. This shows that even a slow-rotating planet with a dense atmosphere, can couple surface and sky in ways that carry energy upward. Radar brightness over mountains points to chemistry at altitude, while gravity waves above those mountains point to dynamics. Both kinds of evidence reduce guesswork. They tie the maps of the ground to the motions of the air. They also help set where to place instruments for future missions. Over bright highlands to study condensation chemistry, along wave-rich regions to probe energy transport, and across corona-rich provinces to search for thermal anomalies linked to activity below. Interpreting the scarcity of craters depends on impact rates and resurfacing. If impacts arrive at a known average rate, then counting craters gives an average surface age. On Venus, the counts suggest a surface that is, on average, a few 100 million years old. That does not require that all lava appeared at once. It can come from widespread but staggered events. Still, some studies have proposed a catastrophic pulse that resurfaced much of the planet in a geologically short interval. Distinguishing between steady and episodic processes is a priority because it connects surface patterns to the way heat escapes from the interior. Near-infrared windows let a little of the surface's heat leak through the clouds on the night side. Orbiters can point at those wavelengths and watch for patches that look slightly warmer or cooler than expected. Differences can come from rock type, surface roughness, or young lava that holds heat longer. The signals are faint and the atmosphere filters them, so the work is hard, but it is one of the few ways to monitor change without landing. The case for active volcanism is strongest when clues agree. A vent that changes shape in radar maps, a local brightening in those thermal windows, and a rise in sulfur dioxide above the same spot, lined up in time and location, make a better argument than any single hint. Upcoming missions with sharper radar, cleaner infrared spectra, and repeat coverage will tighten those tests. Venus sits close enough that spacecraft can fly low and map the same regions often. The highlands raise a separate question: composition. Are they the same basalt as the plains, just lifted and altered, or more silica-rich, like some continental rocks on Earth? With no samples, the answer is indirect. Radar backscatter depends on roughness and the dielectric properties of the rock. Thermal emissivity depends on mineral mix. Taken together, these measurements suggest some highlands may differ from the plains, but the result is not settled. A real difference would point to varied melting and processing in Venus's mantle. High in the atmosphere, the winds behave with unusual consistency. Instead of many storm tracks that shift by season and latitude, the top cloud deck moves almost as one, racing west to east around the planet in just a few Earth days. This super rotation laps the slow, backward spinning ground again and again. From the surface, the sun would be a dim, flattened disk in the haze, while unseen streams above pull the clouds at jetliner speeds. Near the ground, the air barely stirs. Both layers belong to the same system. By moving heat so quickly, the winds smooth out temperature everywhere, leaving little difference between day and night or pole and equator. Chemistry rides these winds. Sulfur dioxide and other gases that rise from lower layers get swept around the globe and mixed into the sulfuric acid clouds. The atmosphere becomes a blender that keeps ingredients stirred, so samples from one place tell a wider story. Models point to waves driven by sunlight and the slow rotation as a way to push angular momentum upward, speeding the flow until it maintains itself. Planet-scale tides in the air and turbulence add to the push. The full picture is still under study, but the main result is clear in images and measurements. A steady ring of motion at the top of the atmosphere linked to a sluggish surface below. The possibility of lightning inside that permanent cloud deck has drawn attention for decades. Direct pictures of bolts do not exist because visible light cannot reach us from within the haze. Yet several missions have recorded signals that look like electrical activity. Early Venera probes detected bursts of radio noise during descent short spikes, similar to those from lightning on Earth. The Pioneer Venus Orbiter and later Venus Express measured low-frequency waves called whistlers, also associated with lightning in our air. These are indirect signs, and some scientists argue for other sources, such as the solar wind interacting with the upper atmosphere or turbulence unrelated to charge separation. The cloud chemistry is different too. On Earth, collisions of water droplets and ice in tall thunderclouds help build electrical charge. On Venus, sulfuric acid droplets would have to play that role, or ash and dust from eruptions could seed charge. If discharges happen, the dense air would likely stretch the glow of each event, making flashes slower and more diffuse than the sharp forks we know. From the surface, a strike would not carve a bright path through clear air. It would light the haze as a muted sheet and fade. Even without confirmed bolts, the search matters because lightning can change atmospheric chemistry. On Earth, it helps produce nitrogen compounds. On Venus, discharges could shift sulfur and carbon pathways, making short-lived molecules that affect the cloud layers. Instruments designed to catch both radio signals and faint optical glows will try to settle the question on future missions. The answer feeds back into climate models because chemistry and radiation together set cloud thickness and reflectivity. Any hardware that enters those clouds faces difficult conditions. Droplets of sulfuric acid attack coatings, windows, and seals. The haze reduces contrast, so cameras struggle to resolve features. Charged particles and strong winds jostle sensors. Designers add acid-resistant layers and rely on short operating times. Most probes have worked for hours, not weeks, in the upper air before power or materials fail. Even so, the data have mapped wind speeds, particle sizes in the cloud decks, and changes in sulfur dioxide with height. These profiles show a layered atmosphere that is active but steady, with patterns that repeat and can be modeled. Seeing the surface required radio waves. Synthetic aperture radar, or SAR, can send pulses through the clouds, reflect them from the ground, and use the returning signal to form images. NASA's Magellan spacecraft, launched in 1989 and arriving in 1990, used SAR to map almost the entire planet at high resolution. The craft was not a large flagship. It was built from spare parts and focused on one main instrument. That focus paid off. The maps that came back replaced guesses with measurements. Plains of basalt covering most of the surface, long sinuous lava channels, shield volcanoes, and circular features called coronae. The low number of impact craters showed that the surface is geologically young on average, likely a few 100 million years old, meaning volcanism or other processes have resurfaced wide areas in relatively recent time. Volcanic landforms dominate. Broad shield volcanoes rise gently, where hot material from deep inside reaches the surface in fixed spots. Mahat Mons stands among the largest, reaching about 8 kilometers above its surroundings and spreading across a region large enough to cover a nation. Pancake domes mark places where thick lava oozed out and spread as flat mounds with sharp edges. Coronae form rings hundreds of kilometers wide, probably where upwelling pushed the crust upward and then let it settle and fracture. Wrinkle ridges crisscross the plains like puckers in cooling skin. In several areas, radar images taken at different times suggest changes in vents and flows that could be signs of recent eruptions. Measurements of sulfur dioxide above the clouds have varied as well, which may match bursts from active sources below. A few narrow windows in the near-infrared LED instruments glimpse the planet's own thermal glow on the night side. Variations there may indicate patches of warmer rock. None of these clues alone is proof, but together they keep open the case for ongoing activity. Mountains add detail to the map and to the chemistry. Maxwell Montes, near the north, rises nearly 11 kilometers above the average level. In radar images, high peaks appear unusually bright. Snow cannot form there, but metallic compounds can condense under those temperatures and pressures. Lead sulfide and other candidates fit the conditions and would reflect radio waves strongly, creating a kind of metallic frost. This is not decoration. It is a phase change of materials that are stable at altitude. The observation ties local temperature, pressure, and composition to a direct signal in the data. Some of the most rugged terrain takes the form of tesserae regions cut by intersecting ridges and valleys. Their complex patterns suggest long histories of compression and extension in different directions. They likely predate large lava floods that reset much of the planet, making them windows into deeper time. Because Venus lacks the plate boundaries that set patterns on Earth, these old patches record stresses in a single, mostly unbroken shell. How they formed remains under study. They may mark where the lithosphere thickened and buckled, or where mantle upwelling pushed and stretched the crust before lava buried the edges. Large highland blocks called Ishtar Terra and Aphrodite Terra rise far above the plains. Ishtar Terra, roughly the size of Australia, holds Maxwell Montes and other rugged features with bright radar returns that hint at different materials or rougher textures. Aphrodite Terra stretches more than 10,000 kilometers along the equator, with a mix of ridges and fractured blocks that point to broad uplift and extension. On Earth, continents float as lighter crust carried by moving plates. On Venus, with no clear signs of plates that dive and collide, such highlands likely formed by plumes that swell the crust or by thickening and crumpling of a strong lithosphere. Similar shapes do not require the same origins. The difference in tectonics may trace back to water. On Earth, water weakens rocks at depth and helps faults move, making it easier for the crust to break into plates that slide and recycle. Without oceans and with higher surface temperatures, Venus's lithosphere appears stronger and more continuous. Heat then escapes in pulses and sheets rather than along long-lived boundaries. A world can reach the same end cooling its interior, but take another path to get there. Counting impact craters gives a rough average age for the surface if the impact rate is known. Venus's crater counts point to a surface that is, on average, a few 100 million years old. This does not require a single catastrophic resurfacing. It could be the sum of many events. Still, some studies argue for a major episode that flooded much of the planet in a geologically short time. Distinguishing between episodic and ongoing renewal is a key task. It connects surface patterns to how heat moves from the mantle to the crust. There is also a direct link between mountains and the winds aloft. When fast flow moves over high terrain, it can generate atmospheric gravity waves that rise and leave ripple-like signatures all the way to the cloud tops. Spacecraft have observed large, stationary wave patterns parked over highlands, evidence that the surface can send signals upward through the thick air. These waves affect temperature and wind structure and may help distribute momentum in the super-rotating flow. They also point to specific sites worth revisiting with focused instruments. Operating near Venus demands different engineering choices than missions to Mars or the Moon. At the surface, survival is measured in minutes to hours. Pressure vessels must hold back 90 atmospheres. Heat must be delayed with insulation, phase change materials, or active cooling that consumes mass and power. Windows and sensors need acid-resistant coatings, yet coatings can fog under attack from droplets. Bearings and lubricants fail at high temperatures, so mechanisms must be simple and robust or eliminated. In the clouds, balloons can float at altitudes where pressure and temperature are closer to Earth's, extending lifetimes. But every exposed surface must still resist acid. Communications must pass through a scattering, absorbing medium. Each design is a set of trade-offs made against the known limits. The Venera program showed what is possible under those limits. Early attempts failed en route or during descent, but the lessons stacked up. Venera 4 returned the first in-situ atmospheric data from another planet and showed that the air was far denser and hotter than many had expected. Venera 7 reached the ground and sent data for minutes from the surface, an engineering and operations success at a time when basic survival under such conditions was unproven. Venera 9 and 10 returned the first pictures from the surface, blocky rocks under a low, hazy sky with the horizon bent by refraction in the dense air. Venera 13 lasted over 2 hours, sending color views and analyzing soil with an onboard instrument. The pictures showed an orange-brown landscape under a yellow sky, with flat, layered rocks and a dim light that still came from the sun filtered through acid clouds. Microphones recorded a steady, low wind in air so heavy that even a slow flow carries weight. Magellan's global maps completed the first survey. After mapping, the spacecraft performed controlled dips into the upper atmosphere to change its orbit, a process called aerobraking. The technique demonstrated that even Venus's air can be used as a tool. It reduced the amount of fuel needed and left more time for radar passes. The end result was a near-complete image of the surface at scales, fine enough to trace lava channels and faults. That dataset still anchors studies of Venusian geology and guides where future missions will look for change. Cloud physics ties back to what telescopes can see from far away. Droplet size and number set how light is scattered and absorbed. Spectra measured from Earth or from orbiting observatories carry the imprint of those sizes. Matching models to those spectra gives droplet distributions and layer heights. The same approach applies to exoplanets. Many of the rocky worlds found near other stars will be too hot for water clouds and may develop thick hazes from other chemistries. Venus provides a nearby example where the physics can be tested against in situ and remote data, then applied to distant cases where only starlight filtered through an atmosphere is available. The uniformity of temperature at the surface comes directly from the way superrotation and dense air move heat. Fast winds at high altitude redistribute energy quickly. The lower atmosphere conducts and convects heat around obstacles, so mountains and plains end up at nearly the same temperature. Night does not offer relief because the greenhouse effect blocks efficient cooling. The result is a planet where local weather at the ground is more about clouds far above than about fronts or storms in the air you would breathe. A small number of near-infrared windows allow instruments to view the night-side glow from the ground through narrow bands where carbon dioxide absorbs less. Observations through these windows have hinted at differences in emissivity, the ability of the surface to emit heat that could indicate different rock types or fresh flows. Combined with radar roughness and reflectivity, these hints may help map composition from orbit. If highlands showed different emissivity than plains, it could mean richer silica content in some regions, a clue to how the crust formed and evolved. The steady ring of fast wind explains another long-standing observation. Venus's cloud tops show long streaks aligned with the flow, and the planet presents a consistent ultraviolet pattern in images. Darker and lighter bands arise from variations in unknown absorbers mixed with sulfuric acid droplets. Identifying those absorbers remains an open problem. They matter because they control how sunlight heats the upper layers, which in turn affects the strength and structure of the winds. Sampling at specific heights with modern instruments could isolate the chemistry and feed back into circulation models. Over 4 years, Magellan circled Venus nearly 5,000 times and stitched together a near-global map. By 1994, it had imaged about 98% of the surface. The view beneath the clouds turned out to be varied and active in form: mountains, broad plains, sinuous channels, and many volcanic structures. Radar does not return color the way a camera does. It measures texture and reflectivity. Even so, the images were clear enough to trace ridges, see collapsed pits, and follow flows that once moved across open ground. Patterns in brightness showed where surfaces are rough or smooth, fresh or weathered at radar scales. Volcanism stood out in both number and scale. Magellan counted well over 100 large volcanoes and many more small cones and domes. Shield volcanoes spread gently, built by repeated fluid flows. Steeper, more complex edifices rose, where thicker lava piled up. A distinctive type, called a pancake dome, formed when viscous lava oozed outward and froze as flat, circular mounds with sharp rims. Many of these are tens of kilometers across. They look geometric in plan view because the lava did not run far before solidifying. Nearby, long lava channels, some hundreds of kilometers in length, show that other eruptions produced very fluid flows, able to cut paths and drain across low ground before cooling. Large circular features called coronae mark places, where hot material pushed upward from the mantle. A typical corona spans hundreds of kilometers and shows rings of fractures, ridges, and a sagging interior. The pattern suggests uplift followed by collapse as support faded, with magma intrusions and faulting reshaping the crust more than once. Coronae appear in clusters and belts, hinting at widespread mantle processes rather than isolated events. Where corona belts cross plains, wrinkle ridges and graben add a secondary fabric, as if the surface puckered and stretched after cooling. Vast plains of basalt cover most of the planet. These plains record eruptions that poured out sheet after sheet of lava, burying earlier terrain and smoothing older relief. Impact craters are relatively scarce and often look fresh because erosion by liquid water does not act here. The crater count implies that much of the surface was renewed within the last few 100 million years. Whether this renewal came in steady episodes or in one or more short pulses remains under study. In either case, flows were extensive enough to repave large regions and to erase many older marks. Fractures and faults form networks that cut across plains and into highlands. Some regions show long rifts, where the crust stretched and thinned. Others host densely cross-cut terrain called tesserae. Tesserae stand higher than surrounding plains and reflect radar strongly because of complex topography at small scales. Their intersecting ridges and troughs indicate multiple stress directions over time: compression, extension, and shear in changing order. Because lava later buried wide areas, tesserae likely preserve some of the oldest exposed surfaces on the planet. Mountains rise above this volcanic background. Maxwell Montes, near high northern latitudes, stands roughly 11 kilometers above the mean level. Peaks in this range are bright to radar, not from ice, but likely from thin coatings of materials that condense at altitude under Venus conditions, such as lead or bismuth sulfides. These coatings change the dielectric properties of the rock and increase backscatter. Other uplands show bright caps as well, tying surface chemistry to altitude and temperature bands. Magellan's technique was straightforward in concept and demanding in practice. Synthetic aperture radar sent pulses through the clouds, recorded echoes from the ground, and combined many passes to raise resolution. Side-looking geometry created shadows and layover that scientists learned to read as slope, height, and roughness. Repeat tracks allowed slight angle changes that helped separate lighting effects from real texture. In the 1,990 seconds, this was a major demonstration that radio mapping can expose hidden landscapes, a method later used and adapted for other worlds with thick air or icy shells. Hints of modern activity appear in multiple datasets. Some vents, imaged at different times, show shape or brightness changes that fit new or altered flows. Near-infrared windows in the atmosphere let instruments sample the planet's own thermal glow on the night side. Small anomalies there could be fresh surfaces cooling differently from older rock. Measurements of sulfur dioxide above the clouds have varied across years, which could match bursts from eruptions. Each line of evidence has uncertainties in calibration and interpretation, but together they keep interest focused on specific volcanic provinces. Highland blocks the size of continents on Earth. Ishtar Terra and Aphrodite Terra anchor the global map. Ishtar, roughly Australia-sized, holds Maxwell Montes and rugged plateaus cut by faults. Aphrodite stretches along the equator for more than 10,000 kilometers, with ridges, rifts, and blocky uplifts that suggest broad forces lifting and pulling the crust. On Earth, continents ride on moving plates and consist of buoyant, silica-rich crust. Venus shows highlands without clear evidence of plate motions. Mantle plumes may have thickened and swelled the lithosphere locally. Long-term horizontal stresses in a strong shell may have crumpled and raised plateaus without subduction. Similar shapes do not require the same origin. As Magellan finished mapping, engineers used aerobraking controlled dips into the upper atmosphere to change the orbit and improve coverage. The spacecraft then entered the atmosphere and burned up after completing its plan. The maps remain the default base for geologic work on Venus. They guide where to point new instruments, where to look for change, and where to sample winds above terrain that launches large atmospheric waves. The idea that Venus's upper air could host long-duration missions grew from simple numbers. At altitudes between about 50 and 60 kilometers, pressure is near 1 bar, and temperatures range roughly from 20 to 30 degrees Celsius. Radiation levels are lower than on an airless surface because kilometers of gas sit overhead. The challenge is chemistry, droplets of sulfuric acid, and a dry mix of carbon dioxide with traces of other gases. In that layer, a balloon filled with nitrogen, oxygen, air would be buoyant because the surrounding gas is heavier. Designs trade among materials, coatings, lifting shapes, and payload mass to find workable combinations. A study concept often cited is HAVOC, the high-altitude Venus operational concept. It sketched crude and robotic missions that would deploy large, helium or air-filled aerostats with gondolas or pressurized modules hanging beneath. Crews would live for days to weeks, ride the zonal winds, and conduct sampling and remote sensing. Instruments could collect cloud particles, measure droplet sizes, identify unknown ultraviolet absorbers, and make wind profiles through repeated drops and climbs. Radar sounders and compact SAR could map targeted swaths below with finer detail than earlier surveys. Materials drive feasibility. Polymers must resist acid for long periods. Composites and metals need coatings that do not crack under UV and thermal cycling. Windows and optics require protective layers that maintain clarity in a mist that tries to etch every surface. Power is available from solar panels, but sunlight is reduced and reddened by the clouds. Designs add high-efficiency arrays and energy storage sized for days of operation at constant load. Communications pass through scattering air. Relay orbits and high-gain antennas keep data rates useful. Motion is not optional at these heights. Winds at the cloud tops circle the globe in about 4 Earth days. A platform will drift with that flow. Steering is possible by changing altitude into layers with different speeds, by shifting lift in an asymmetric hull, or by using small propulsors. But the dominant motion remains set by the atmosphere. Mission plans accept global laps and schedule observations by longitude bands encountered on each circuit. Sampling in the clouds addresses chemistry and, potentially, biology. Water activity, the measure of available liquid water, is low in sulfuric acid droplets, which is a strong limit for life as we know it. Some mixtures could raise water activity in microenvironments within droplets, and some terrestrial microbes tolerate acid by forming protective layers or by living inside particles. Instruments can test pH, water activity, and organics at the scale of single droplets. Results would speak to whether complex chemistry persists at these heights and how long particles last before evaporating or merging. Data gathered aloft also improve models of superrotation. Wind profiles, temperature soundings, and wave signatures near mountain chains directly test how momentum moves from lower to higher levels. Stationary gravity waves over highlands have been seen from orbit as large arcs in cloud-top brightness. In situ sensors can resolve their wavelengths and amplitudes and link them to terrain. Those measurements answer how much these waves contribute to keeping the fast flow alive. Floating platforms can carry compact radar to refresh surface maps. Night-side observations in infrared windows benefit from shorter atmospheric paths when viewed from above the cloud decks. Combining these datasets refines estimates of rock types and flags places where emissivity or roughness changed. If plume-fed provinces still vent heat, hot patches may appear and fade over months to years. Repeated passes build time series that can catch such changes. The idea of long-term human presence in this layer remains speculative, but it aligns with simple physics. A breathable mix is buoyant, temperatures are mild, and pressure is familiar. The blockers are steady exposure to acid and the need for reliable, light power systems. Even without crews, robotic aerostats that last months would return dense records of winds, chemistry, and cloud microphysics, and would serve as relays for short-lived landers below. Before radar and balloons, Venus lived in stories. Civilizations tracked its cycle as morning and evening star because it never strays far from the sun in our sky. In Mesopotamia, it was linked to Inanna or Ishtar, deities tied to love and war. Tablets recorded its risings and settings with care. In Greece, it became Aphrodite. In Rome, Venus. In Mesoamerica, Maya astronomers recorded its synodic period in the Dresden Codex and used its returns as calendar markers. Across Polynesia, navigators used its brightness near dawn or dusk to set bearings on long ocean crossings. In China, it was the Great White Star. part of a 5-planet scheme linked to elements. In Japan, it appears in poetry as a sign of renewal. The common thread was visibility and regularity. From any open horizon, the planet is easy to pick out. It repeats a clear cycle, shifting from evening to morning object over months, then back again. The same visible cycle that supported myth also provided the first tests of heliocentric models. Through a small telescope, phases reveal that Venus orbits the Sun and not Earth. That phase sequence, measured and drawn centuries ago, fits the current orbital geometry used by mission planners. Modern images and numbers change the content of the stories without removing the source. Under the clouds, there are plains of basalt, long channels, and highlands, raised without the familiar framework of shifting plates. Above, there are sulfuric acid clouds, a dense carbon dioxide atmosphere, and fast winds at the top that carry the sky around in days, while the ground rotates slowly in the opposite direction. Instruments that ride through the cloud decks find layers, droplets, and winds that keep their pattern with little seasonal change. Radar echoes outline mountains that shine to radio waves because of coatings at altitude. Near-infrared windows show small differences in surface glow that may flag fresh flows. Plans now point to focused observations. Track unknown ultraviolet absorbers that set cloud-top contrast. Map gravity waves over high terrain. Watch specific vents for thermal change. Sample droplet chemistry, where models disagree. Test how often sulfur dioxide spikes and how fast it mixes. Each target comes from gaps left by earlier missions and from the constraints of working through an atmosphere that hides the ground from ordinary light. On Earth, the greenhouse effect keeps the surface warm enough for liquid water. A greenhouse gas is any gas that traps heat radiated by the ground. The main ones here are water vapor, carbon dioxide, and methane. They let sunlight in and slow the escape of infrared energy back to space. With no greenhouse effect, Earth would be a frozen world. With a moderate one, oceans, forests, and people can exist. On Venus, the same physics runs at a far larger scale. Carbon dioxide is not a trace gas there. It is the air itself, making up more than 96% of the atmosphere. Pressure at the ground is about 90 times Earth's sea level. Sunlight warms the surface radiates heat, and the carbon dioxide blanket absorbs and re-emits that heat many times before a small part escapes to space. The result is a planet locked near 460 degrees Celsius. The greenhouse effect that helps Earth is the effect that dominates Venus. The contrast begins with amounts and sinks. On Earth, carbon dioxide is measured in parts per million, and large reservoirs remove and return it over time. Oceans dissolve CO2 and store it. Weathering binds it into carbonate rocks. Plate tectonics and volcanoes move carbon between surface and interior. Plants and microbes draw it down and release it again. These linked cycles set limits on temperature swings and help buffer natural changes. On Venus, the ocean reservoir is gone, so there is no large, quick sink. Without plate tectonics like Earth's, the slow return of carbon to rock is limited. Without a biosphere, there is no biological drawdown. The same basic physics works, but the boundary conditions are different, and the outcome is extreme. Runaway heating is a feedback story. If early Venus had surface water, warming would have increased evaporation. Water vapor is itself a strong greenhouse gas, so more vapor trapped more heat, which drove still more evaporation. As water reached higher altitudes, ultraviolet light split some molecules, and the light hydrogen escaped to space. Over long spans, this drained the planet of water. With the ocean sink removed, carbon dioxide built up. Once the system crossed certain thresholds, it moved toward a hot, stable state. Earth is not on that path, but the comparison sets scale. A small rise in greenhouse gases here still raises temperature measurably, shifts rainfall patterns, melts ice, and lifts sea level. Planetary physics does not change with location. A carbon dioxide molecule absorbs infrared energy in the same way whether it is over Paris or over Mare Mons on Venus. Studying a nearby high CO2 atmosphere under intense heating tests, models that also apply at smaller effect sizes to our climate. It also illustrates that climate is not fixed background. It is a system that reacts to inputs and feedbacks. Some models of early Venus, using a dimmer young sun and shallow oceans, find long spans with mild temperatures and stable cloud patterns that would have shielded the surface. In those scenarios, liquid water could persist for hundreds of millions of years or more. Evidence that water was once present comes from the ratio of deuterium to hydrogen measured in the atmosphere. Deuterium is a heavier form of hydrogen. When water is lost to space over time, lighter hydrogen escapes more readily, leaving deuterium behind in higher proportion. Venus shows an enriched deuterium ratio compared to Earth, which is consistent with significant water loss. If Venus once held oceans, life in simple forms could have had time to arise. There is no direct evidence for that, and the current surface and air are far outside known limits for biology. The idea matters because it shows how two near-twin planets can follow different tracks based on distance from the Sun, starting water inventory, and feedback. For worlds around other stars, this matters even more. Many rocky exoplanets orbit close to their stars and may carry thick atmospheres. Some will be super Venuses, not shy Earths. Venus helps us read their spectra and sort, which are truly temperate and which have already crossed into hot, stable states. The greenhouse story links back to light and chemistry in a simple way. Energy in must equal energy out over time. On Venus, outgoing infrared is throttled by absorption, so the surface temperature rises until a new balance is reached at higher temperature. On Earth, the same balance holds, but ocean uptake, cloud feedbacks, ice reflectivity, and biosphere processes all modulate the path. That difference in control points is why one planet keeps rivers and seasons, while the other keeps a near uniform furnace. Sound behaves differently in Venus's air. Dense carbon dioxide carries pressure waves faster than air on Earth, roughly twice as fast, but also absorbs high frequencies strongly. If a person could stand there with protection, a voice would sound deeper and slower. A hand clap would become a heavy thump. The atmosphere acts like a filter that mutes sharp, high-pitched sounds and favors low tones, yet there is little to hear. Near the ground, the winds are slow, only a few kilometers per hour, and in such dense air, their motion does not produce the flutter and rustle we know. There are no birds, rivers, or leaves. The background is a steady, low-pressure hum. Soviet Venera landers carried microphones and pressure sensors. The recordings returned a faint, continuous wind. No thunder, no sharp cracks, just a subdued hiss shaped by thick air. The impression is not silence, but suppression. Carbon dioxide density and high temperature smear the edges of every sound. Even a nearby mechanical noise would carry as a low rumble rather than a bright buzz. Ground motion still occurs. Without plate tectonics, Venus does not have the same large subduction or spreading boundaries as Earth, but stress builds and releases. Spacecraft have detected signals consistent with quakes, and some surface features look like faulting and warping. A quake on Venus would send vibrations through hot rock and dense air. The sound would be a low, rolling pressure change rather than a sharp crack. With no cities, forests, or seas to respond, a tremor would pass with little surface drama. Volcanic activity adds another possible source of sound. Radar maps show many vents, shields, fissures, and lava channels. Changes seen in a few vents over time and variations in sulfur dioxide above the clouds suggest that eruptions may still occur. On Earth, gas jets hiss and explosions crack. On Venus, dense air would turn those into heavy booms and broad rumbles. Fine, high-pitched components would be damped. Gas release itself might be near silent to human ears under such pressure, with only the lowest tones carrying. Acoustics connect to simple properties: density, temperature, and gas composition. Carbon dioxide has different absorption bands for sound compared to nitrogen-oxygen air. At Venus conditions, the mean free path, the average distance between molecular collisions, is short. Waves lose energy quickly at high frequencies. This is why the world would feel bass-heavy, and why even a moving rover wheel would likely drone rather than whine. The difference between the quiet at the ground and the speed above links back to vertical structure. At high altitudes, the atmosphere is thinner and moves fast in the super-rotating flow. Near the surface, it is hot and heavy, and motion is slow. That layering shapes both sound and heat. Heat transport is efficient enough to even out temperatures at the ground, but not enough to make the air lively with audible turbulence. The system carries energy more by steady transfer than by gusty mixing where people would stand. The greenhouse contrast returns in another practical way: radiation. On a bare world like the Moon or Mars, cosmic rays and solar particles reach the ground with little shielding. On Venus, kilometers of air mass lie overhead. At cloud level, the radiation environment is far milder than on an airless surface. This matters for balloon and aerostat ideas, and it illustrates again how the same factor, a thick air, can either protect or punish, depending on what you ask it to do. Climate models learn from this range of conditions. The same radiative transfer equations handle weak and strong greenhouse cases. The same fluid dynamics govern slow flows and fast jets. Venus tests the limits. Changes in unknown absorbers at the cloud tops alter ultraviolet patterns and therefore heating. Sulfur cycles set droplet sizes and layer heights, which set reflectivity. Each parameter can be measured or bounded, then fed back into models that also apply to Earth and exoplanets. The story of water loss is a chain that can be followed step by step. As oceans evaporate, more water reaches high altitudes. Ultraviolet light splits H2O into H and O. Hydrogen escapes more readily because it is light. Oxygen reacts with rocks or finds other sinks. The remaining atmosphere becomes dry. With no rain and no ocean chemistry, carbon stays in the air as CO2. The deuterium enrichment is the chemical clue left behind, a simple ratio that keeps record of a long escape process. If early Venus had shallow seas under a dimmer sun, the sky would have included water clouds that reflect light and limit heating at the surface. As brightness rose with stellar aging, those clouds would change. Once evaporation outran rain return, the greenhouse feedback would strengthen until surface water could not survive. The transition need not be dramatic from a daily point of view. It could be a slow drift over millions of years. The end state is the same: thick, CO2, hot air, and a dry ground. On Earth, the Ocean Rock Life Partnership acts as a brake. Weathering of fresh rock draws down CO2 and ends in carbonate deposits. Subduction carries those rocks inward, and volcanoes release CO2 back to the air. Plants and microbes shift the balance toward organic storage and oxygen release. Ice and cloud feedbacks add control points. None of these loops alone explains stability. Together, they do. The key difference is the presence of water over geologic time and the existence of plate motions that keep the cycles running. Many exoplanets sampled by current telescopes lie close to their stars. Some are rocky and similar in size to Earth and Venus. Their spectra sometimes show thick atmospheres and high temperatures. When those planets are labeled potentially habitable based only on size and distance, Venus serves as a check. A world can meet those broad rules and still be too hot once feedbacks and history are included. Interpreting a spectrum needs a template, and Venus is the nearest hot template we have. At ground level, the sensory mix would be simple: dim light, high temperature, high pressure, and altered sound. The sky would be a yellow-orange haze with soft shadows. The sun would appear as a pale disk. Distant features would blur. Underfoot, basalt blocks and plains would hold steady heat. The air would press on every surface. A microphone would hear a low, continuous tone, with occasional small changes as a gentle wind passed. A seismometer might catch small quakes. A gas sensor would register sulfur dioxide spikes over time if nearby vents released it. None of this requires drama to describe. It flows directly from measured numbers. Carbon dioxide concentration sets infrared opacity. Pressure and temperature set sound, speed, and absorption. Chemistry sets droplet formation, which sets cloud layers and reflectivity. Radar backscatter and thermal emissivity set surface texture and composition clues. Deuterium ratios set water loss histories. Each measurement tightens a piece of the picture and limits guesswork. Venus's past, present, and physics together form a clean comparison with Earth. Similar mass and size, different water history and carbon cycling. Similar mantle processes, different crustal style without moving plates. Similar solar input in broad terms, different outcomes after feedback. For climate, geology, and acoustics, the same equations give two sets of answers when the inputs change. A planet does not need new rules to end in a new state. It needs different starting amounts, different sinks and sources, and time. The acoustic scene links to lightning higher up. If electrical discharges occur within the clouds, and several missions have heard radio signatures that fit those flashes, would be dim sheets in the haze rather than bright forks. Their sound, if any reached the ground, would be a long, muffled rumble. The dense air would slow and stretch the pressure wave. A lander microphone might catch it as a gentle rise and fall, rather than a crack. Quakes and eruptions would add their own low tones. A distant vent spilling lava would not snap and hiss like a terrestrial fire fountain. It would breathe. A fault slip would not ring with brittle pops. It would throb. Between events, the baseline would return. Warm wind in heavy air, a slow, even background. For researchers, the quiet physics of Venus is not a thought experiment, but a set of testable clues. Acoustics in dense carbon dioxide air, quakes in a crust without plate boundaries, and low-frequency rumbles from muted eruptions all become probes of structure and heat flow. Microphones, pressure sensors, and seismometers tell how sound, speed, absorption, and ground coupling change with temperature and pressure. Radio links through haze reveal turbulence and layering. Each instrument translates a subdued environment into measurable signals that show how an atmosphere filters perception, how geology persists without Earth-style tectonics, and how a planet expresses energy with the volume turned down. After years in Mars's spotlight, Venus is again drawing mission plans designed to work through its specific challenges. NASA's Da Vinci Deep Atmosphere, Venus investigation of noble gases, chemistry, and imaging, targets the atmosphere directly. A descent sphere would sample gases from cloud tops to low altitudes, measuring noble gases and isotopes that preserve the planet's origin story, and tracking water, sulfur dioxide, and trace species with altitude. Imaging during breaks in the clouds would capture oblique views of rugged tessera terrain, where intersecting ridges and valleys rise above surrounding plains. The probe would not last long at the surface, but the descent, profile, pressure, temperature, winds, composition would set a vertical framework that orbiters and models can anchor to. Layer by layer chemistry would test ideas about water loss, volcanic outgassing, and the age of the atmosphere. Where Da Vinci follows the air down, a radar mapper like Veritas, Venus, emissivity, radio science, INSAR, topography, and spectroscopy focuses on the ground from orbit. Interferometric radar, INSAR, could detect subtle changes in surface elevation that hint at active uplift or settling. High-resolution topography would resolve small vents, collapsed pits, and flow margins. Night-side spectroscopy within near-infrared windows would compare the thermal glow of different rock units, flagging fresh basalt where emissivity differs from older, weathered plains. Radio science tracking of the spacecraft's motion would refine the gravity field, linking mass anomalies to buried structures such as large coronae roots or mantle upwellings. Together, these methods aim at a core question: is Venus still reshaping its surface today? ESA's InVision complements that approach with its own radar and spectral payloads. By combining repeat-pass radar imaging with targeted spectral snapshots, it can revisit candidate volcanoes, fault systems, and tessera blocks on multiple orbits, building time series that catch change rather than a single frozen frame. Atmospheric instruments ride along to tie surface regions to cloud behavior, gravity waves parked over highlands, sulfur dioxide plumes above suspected vents, and ultraviolet patterns set by unknown absorbers that heat the upper layers. Cross-calibration with the descent probe's profiles would let teams connect chemistry at specific heights to terrain directly below. The scientific pull is straightforward. Two near-twin planets, Earth and Venus, share mass, size, and bulk composition, yet diverged sharply. To explain that split, missions target missing numbers: the exact noble gas mix that encodes early degassing, the altitude by altitude water content, the present-day outgassing rate, the age spread of lava plains, and the mechanics of uplift in highlands that rose without drifting plates. Each measurement trims uncertainty around feedbacks that link air, rock, and heat. For climate models on Earth, a high CO2, high-pressure atmosphere nearby is an external check on radiative transfer and cloud microphysics. For geodynamics, Venus shows how a rocky world cools and vents when oceans do not lubricate faults and when plates never break and dive. A return to Venus also maps onto practical engineering. Descent spheres must survive acid droplets and steep thermal gradients as they fall. Sensors need windows immune to etching, coatings that keep optics clear, and pressure housings that hold shape under 90 atmospheres. Orbiters working radar through dense air must manage signal loss, clutter from multiple scattering, and thermal cycling near the planet's hot limb. Aero-braking in thick upper layers can trade fuel for data but demands precise control. Balloons or aerostats in the temperate cloud deck offer long lifetimes for chemistry and wind tracking, with corrosion-resistant skins and power budgets sized for filtered sunlight. The technology path itself becomes part of the science, because platforms at different heights sample different regimes of motion and composition. Beyond immediate goals, Venus helps set context for rocky planets as a group. Consider the 4 inner worlds side by side. Mercury, smallest and closest to the Sun, carries almost no air. Daylight bakes exposed rock. Night radiates heat straight to space. Temperature swings are enormous because nothing stores and spreads energy. Venus sits only a bit farther out, but carries the opposite condition, a massive carbon dioxide blanket that traps heat and levels it across day, night, pole, and equator. Earth, similar in size to Venus, keeps oceans and moving plates that move carbon between air, water, and stone, and a biosphere that joins the cycle. Mars, smaller and colder, lost much of its air to space, and now holds water as ice and brine, with winds that sculpt dust but little capacity to warm the ground with greenhouse gases. 4 outcomes from the same starting materials, differences in mass, distance, and feedbacks decide whether a planet swings, bakes, balances, or thins. Placed against that set, Venus highlights boundary behavior. Its slow, retrograde rotation and super-rotating upper winds break Earth-based intuitions about day length and weather. Its continent-sized highlands, Ishtar Terra and Aphrodite Terra, stand without clear signs of subduction. Its plains are lava-built and relatively young by crater counts, but the style of renewal may be episodic rather than constant. Its cloud decks hide unknown ultraviolet absorbers that control heating where the fast winds blow. Each point is a reminder that, Earth-like in size, is not enough to predict climate, crust, or circulation. That warning scales to exoplanets. Surveys around other stars find many rocky worlds near their suns. Some are placed where simple models would allow surface water, yet spectra that show thick cloud and high CO2 may point to hot, stable states rather than mild ones. Astronomers now use Venus Zone to describe orbits where starlight and greenhouse feedbacks are likely to dry and heat a planet into a runaway. Templates built from Venus, cloud layer heights, droplet sizes, sulfur cycles, thermal windows, and super-rotation speeds become tools for reading faint signals in starlight. With those tools, a bright, cloudy planet of Earth size can be sorted as temperate or already past the point where water persists. Comparisons with Mercury and Mars sharpen the role of size and air. Mercury's heat is exposure without insulation. Venus's heat is insulation without relief. Mars's cold is loss of air. Venus's uniform heat is excess of air. Earth occupies a mid-state where sinks and sources offset enough to keep liquid water. In that mid-state, soundscapes, weather, erosion, and biology are all consequences of pressure and phase. Venus shows how those same processes alter when pressure is high and water is absent. Erosion slows, acoustics deepen, mountains grow bright to radar, from metallic frost rather than white with snow, and lightning, if present, glows as sheets within acid haze. Missions tuned to these contrasts push for specific tests. A descent probe's isotope ratios can bracket how much water escaped and when. Noble gases such as xenon and argon carry records of outgassing and loss that do not reset easily. Vertical profiles of sulfur dioxide and water clarify where clouds form, how droplets grow, and how fast gases mix inputs that fix cloud altitude and thickness in circulation models. Repeat pass radar can catch ground motion near vents or over coronae rims at centimeter scales. Night-side spectroscopy through infrared windows can flag thermal anomalies that match radar bright flows. Radio occultations watching a signal pass through the limb of the atmosphere yield temperature and density with height and track waves that climb over highlands. The engineering logic of aerostats at 50 to 60 kilometers connects chemistry and dynamics directly. In that layer, pressure and temperature are close to familiar values, but the droplets are sulfuric acid and water activity is low. Sample cells can measure pH, water activity, and organics at droplet scale. Wind, veins, and GPS-class navigation can map speed and direction. LiDARs can profile aerosol layers above and below. By changing altitude to tap layers with different flow, a platform can step between jets and build vertical shears that test super-rotation maintenance. A small radar sounder can ping the surface and measure echo strength variations with viewing angle, a way to infer roughness and dielectric properties that tie back to rock type or coatings. As the new missions map, sample, and listen, cultural threads follow in parallel. For most of history, the bright point near dusk and dawn was a sign first and a planet second. In Mesopotamia, it linked to Inanna, Ishtar, a figure of love and war, whose dual nature matched the planet's two apparitions. In Greece and Rome, it became Aphrodite and Venus, symbols of beauty and fertility. Maya astronomers tracked its synodic cycle in tables that timed rituals and recorded rulers' deeds. Polynesian navigators used its brightness near the horizon as a stable mark on long ocean passages. In China, it was the Great White Star, tied to the element metal and the regularities of heaven. The same visibility that invited poetry also invited measurement, from careful naked-eye logs to telescopic phases that confirmed a sun-centered system. That history now sits beside a measured world of carbon dioxide, acid droplets, and basalt plains. The brightness that drew myth comes from clouds that reflect sunlight efficiently. The steadiness that invited omens comes from an orbit that repeats predictably. Under the veil are radar-bright high peaks with metallic frost, tessera blocks that predate wide floods of lava, and long channels that trace low-viscosity flows across open ground. At altitude are fast jets that circle in days, gravity waves anchored over mountains, and ultraviolet patterns set by still uncertain absorbers. At the ground are low winds in heavy air, altered sound, and temperatures that keep metals near their melting points. Instruments tuned to the present questions aim at small, crisp answers instead of broad labels. Unknown absorbers at the cloud tops can be narrowed by spectra from ultraviolet to near-infrared. Sulfur cycles can be timed by watching how quickly a burst of SO2 dilutes with height and longitude. Candidate vents can be placed on watch lists for repeat radar and thermal passes. If INSAR sees subtle uplift at a corona, while near-infrared windows show fresh emissivity, and the air above shows sulfur changes, 3 lines converge on activity. If tessera blocks show emissivity values that differ from basaltic plains, composition may vary, opening a path towards silica-richer rocks in some highlands. If noble gas ratios match specific outgassing histories, interior models can fix how much heat Venus still sheds. Across these efforts, the planet remains close enough for frequent looks and varied platforms. A single map is no longer the goal. Sequences of maps and profiles that capture change are. A single descent is a start. Multiple entries at different longitudes and local times would show how chemistry, temperature, and winds vary across the globe. Balloons at cloud level give days to weeks of data. Small drop sondes can peel off and profile layers on command. Radargrams stack into time-lapse. Spectra accumulate into seasonal curves. Microphones turn pressure into audio that catches waves moving through air dense enough to carry bass, but quick to swallow treble. Set against Mercury's naked rock, Mars's thin chill, and Earth's balanced cycles, Venus occupies the hot, heavy end of the terrestrial spectrum. The missions now queuing do not aim to soften that picture. They aim to resolve it. They press for numbers that tie a bright evening star to isotope ratios, droplet sizes, uplift rates, and wind shears. They test whether vents still warm the night side through narrow windows, whether gravity waves over mountains feed the super-rotating jets, and whether ancient tessera blocks carry a composition different from the seas of basalt around them. The same sky that once served as a calendar marker for sailors and farmers now serves as a laboratory for heat, motion, and rock under conditions a human ear would hear as low and a human eye would see as gold through haze. Curiosity tends to tighten its grip when a simple picture breaks. Venus did that. It looked gentle from far away and turned out to be harsh up close, and that contrast pulled us in. Engineers kept sending machines that would fail by design, because even a few minutes of truth under that sky were worth years of work. Thick shells, pressure valves, acid-resistant coatings, clocks counting down inside ovens, each lander was a small wager placed against a world that does not forgive mistakes. The result was not a long survey with comfort and routine. It was a handful of hard-won numbers that changed the frame. Air made of carbon dioxide, pressure like the deep ocean, temperatures that keep metals soft, clouds of sulfuric acid, winds that barely move at the ground, yet race above the clouds in days. The map that followed from orbit replaced guesswork with patterns. Radar showed plains built by lava, channels that run for hundreds of kilometers, and ringed scars where hot rock pushed up and settled back down. Highlands rose without the signatures of drifting plates. Peaks glowed to radio waves because chemistry changes with altitude. A few vents looked different across repeated passes. Nightside glows through narrow infrared windows hinted at patches that might be younger or hotter than their surroundings. None of this depended on legend. It was visible in returns and ratios, in echoes, in spectra. The new missions take those threads and aim to tie them down. A descent probe can walk a thermometer and a mass spectrometer through the atmosphere and write the vertical story of temperature, wind, water, sulfur dioxide, and noble gases. A radar mapper can look again with finer resolution and with interferometry to catch motion at the centimeter scale. A spectrometer tuned to the right bands can read the surface's own heat after dark and tell one rock unit from another. A radio link bent by the limb of the planet can turn into a profile of density and temperature with height. These are plain tools aimed at plain questions. How much water was there? And when did it leave? How does carbon move now? Where does heat escape? Which vents still breathe? Set beside these plans is the simple geometry of the sky. Venus still refuses to stray far from the sun in our view. It appears, near the horizon, at dusk and dawn, bright and steady, often the first light seen by a child who learns the word star before learning what a planet is. That steadiness is a guide history leaned on. Farmers and sailors watched it as a clock. Priests and poets watched it as a sign. Navigators on open ocean held it in their mental maps. When telescopes arrived, its phases told a new story, that it orbits the sun and shares the sky's stage with Earth in a dance that repeats. Under the clouds, the physics is straightforward. Sunlight warms rock. Rock tries to cool by radiating heat. Carbon dioxide blocks much of that path, sending energy back down and sideways until the whole surface sits at almost the same temperature, day and night, pole and equator. Heavy air carries sound fast but smothers its sharp edges, so claps become thumps and voices sink in pitch. Winds near the ground barely stir, not because energy is low, but because dense air resists quick change. High above, the jets ignore the slow turn of the ground and circle in days. Between those layers, droplets form, fall, and vanish before touching stone. Lightning probably flashes within the haze as slow sheets, more glow than fork, more rumble than crack. The pieces fit because they follow the same rules we apply at home, stretched into a different regime. This is why Venus occupies an important place in climate work. The details differ. The core is the same. A greenhouse gas absorbs in the infrared. Clouds reflect sunlight and trap heat by changing how radiation moves up and down. Chemistry sets what the droplets are made of, which sets how bright the clouds are, which sets how much energy enters and where it is deposited. When you change the amounts and the sinks, you change the outcome. On Earth, oceans, rocks, and life pull carbon from the air and tuck it away for a while. On Venus, the ocean sink is gone. The crust is strong and continuous, and biology never built a feedback that could help. Those differences do not rewrite physics. They rewrite the result. It helps to keep the neighbors in view. Mercury shows what happens without air. Huge swings, sharp days, deep nights. Mars shows what happens when a small world loses much of its air. Cold, thin winds, water confined to ice and brine, traces of a warmer past. Earth shows how a mid-state works. Oceans move heat, plates recycle carbon. Life joins the cycle. Venus marks the hot end. Too much air, too much trapping of heat, and little variation left at the ground. 4 outcomes from one set of basic parts. The lesson scales outward. A rocky planet of the right size near the right distance will not always look like home once history and feedback have their say. From the human side, there is another pattern. We often fall in love with an image before we have the facts. Venus wore that image for centuries. It was tied to gods and to beauty because it deserved the title from our vantage point. Brightest, steadiest, most striking. We filled the unknown with forests and swamps and clouds of water. Then the numbers arrived and swept that picture away. If the story ended there, it would be a bruise. It did not. The replacement is richer. The planet we have now is not simple, not friendly, and not dull. It is a system that gives us leverage on climate, geology, and atmospheres under pressure. It is a place where a microphone hears bass, and a camera sees gold, and a radar sees through. Knowing this does not make its light less. It sets the light against a map and a model and gives it context. Even the idea of visiting adjusts to the facts. We cannot walk the ground for long. We can, however, float where the air is as gentle as a spring day, in pressure and temperature, if not in chemistry. Balloons can sit in that band for days and ride the flow, measure droplet sizes, find the unknown absorbers that paint ultraviolet patterns at the cloud tops, and watch gravity waves park over highlands. They can act as relays for landers that will last an hour, not a season. They can watch the night side for warm spots that come and go. The picture of living with Venus moves up by tens of kilometers, where a human voice would sound mostly normal, inside a sealed cabin, and where the horizon is a sea of amber light that never clears. As for the ground itself, what we have is enough to picture standing there if protection were perfect. The sky would be a dim yellow-orange. The sun would be a pale disk. Shadows would be soft. Rocks would be blocky, layered in places, fractured in others, with surfaces softened not by water but by heat. Distant features would blur. A pressure gauge would read 90 atmospheres. A thermometer would climb toward 460 degrees Celsius and stay there. A wind vane would barely move. A seismometer might twitch now and then. A gas sensor would count sulfur dioxide pulses if a vent lay upwind. A radio would talk to a relay above the clouds and send back data until electronics failed. None of this speaks in one voice because no single part owns the story. Atmosphere and rock share it. Light and chemistry share it. Past and present share it. That is what makes Venus useful beyond itself. It ties fields together and forces simple questions with measured answers. How bright is the cloud deck in ultraviolet? And what does that say about heating at the top? How many noble gas atoms per million sit at 50 kilometers? And what does that say about degassing long ago? How smooth is this flow margin in radar? And what does that say about viscosity? How fast does this gravity wave climb over highlands? And what does that say about momentum in the jets? The planet is not asking us to be poetic. It is asking us to be careful. And yet, the sight that starts all this is still quiet and simple. A bright point appears near the horizon after sunset, or it lingers before dawn. It does not twinkle much. It holds your eye. The same object has done this for every person who ever looked up from a field, a deck, a city, or a desert. The names change, the tools change, the stories change. The cycle does not. That is part of why it works as a touchstone. It means the same thing in two ways at once, constant in the sky and constant as a source of questions. If there is a lesson to carry forward, it is not that Earth will repeat Venus. It will not. It is that balance is a product of parts that can shift. Oceans and stone make a buffer here. Biology helps. Those loops can be weakened or strengthened. Physics is not a sermon. It is a description. Venus is the case where the description lands on heat that does not ease, and air that does not lift, and clouds that do not open. Earth is the case where ocean, rock, and life keep enough room for rivers, snow, and a stable sky. Venus will keep rising in the west after sunset, and in the east before sunrise, bright and patient. Plans will rise with it, probes that fall through acid haze counting atoms, orbiters that sweep radar beams across frozen flows, balloons that drift in the amber and listen to wind and wave. Each return adds a line to a story that does not need drama to hold attention. Numbers and maps are enough. The planet under the veil is proof. When that light appears next time, it will be the same light seen by sailors long gone and by someone yet to be born. It will carry, for anyone who wants it, both a simple joy and a careful map. The joy is in watching it hang over a roofline or a tree. The map is in knowing what sits behind it. A hot plain, a heavy sky, a fast jet at the cloud top, a ringed scar where the crust rose and fell, a mountain bright to radar because chemistry changed with height. The two views do not cancel each other. They fit. One makes the other deeper. Let it be that kind of light in the mind as well. Steady, familiar, and layered with the work it took to understand it. Let it be a reminder that beauty can survive truth, and that truth can sharpen beauty. Then let it slip back toward the horizon, the color softening, the air cooling where you stand, the planet still turning under its veil, and the sky keeping its quiet promise to bring it back again.